Hello. Hello, everybody.
Hello.
Hello, good afternoon.
So we have 5 minutes to do any kind of testing that we need. For example, you want to share? Anybody wants to share the screen?
Yeah, I guess I was one of the people interested in that. So the screen sharing itself should be straightforward.
Right.
But then there's always the question, sharing.
That's beautiful.
Sharing a presentation.
It's a picture. This is
Canadian. Yeah.
Okay,
and
that looks good. Perfect.
Now we have a slideshow. Okay, so then that works. Perfect. And I'll stop sharing.
Yeah. So at the very beginning, I'm going to briefly introduce the two companies with this booklet. So that's how I share the screen, and that's how I stop sharing the screen. Anybody else wants to check things out?
Did Mary or John open this for you? I'm just curious.
It was set up where we couldn't, and then it showed up that we can join at 2:55.
Oh, okay. We're still figuring this out, I guess.
So yeah, it was okay. So okay. Lawrence, is there anything that you want to check or test?
As long as you're sure I'm coming through loud and clear, I'm fine.
Yeah. So you went to school to the University of Manchester, right?
I did. Did you?
Well, no, but can I ask you a question? Is there life on Mars? Is there life on Mars?
Is there life on Mars? Almost certainly.
Okay.
But I never saw any when I was, and it was a long time ago. So
there was a really interesting 2006 TV show, 2 seasons.
Yeah.
Outstanding. Because of Manchester. It was 1973 and then 82. But anyway.
I'd left by then. I left in 1970. So I'm an old man.
Oh, I see. Yes. All right. So who do we have? So the order of presentations is Roman is not here. Clemens, who's number 2. Sonika, she's supposed to connect. And then Lawrence is ending the presentation.
Lawrence has joined twice.
It is allowed.
It is allowed. Okay. You want to get a good seat. Lawrence.
Hello.
Hi, Lawrence. Actually, we hide non-video participants. That puts you away. So we just see your video.
I don't see myself as logged in twice.
No, I did, but I just hid video, but non-video participants, and you went away. And now it's just the video.
It's the way a lot of people like me. Not that.
No, absolutely not. Should I turn this light off?
How many people do we have as spectators?
16 as of right now, but it was 3 a few minutes ago. So now 18 people are connecting.
Adrian, this is Mary. I'm going to make you the host for this meeting. Is that okay?
I think so.
Okay. Unless Jonathan pops in, then I can make him the host.
He's on.
Oh, he is? Okay. I'll make him.
I'll
make him the host.
Perfect.
All right. Thanks.
Yeah. So Sonika is connecting. So we have 3 speakers right now, 22 people. And we're waiting for the first speaker. I'm going to send him a note. He probably will connect shortly.
Hi, Clemens. Nice to meet you. I don't think we've met before.
Yeah, nice to meet everyone.
Are you based in Canada?
Yeah, in Vancouver. Yeah. Or at least in North Vancouver, and now it's all remote. But yeah, it's perfect lunchtime here.
Yeah, it's a nice time of year.
Yeah, it's a beautiful fall, but it's we had a few of these phenomena called atmospheric river, and it is as wet as it sounds.
Oh my goodness.
Interesting. Usually the fall is dry back east, at least.
Yeah, we got the summer really dry and bad. I think the whole west coast of the North American continent had that. So good to see some of that coming back and making sure nothing dries up too much.
Yeah, life requires water.
Yeah.
Okay, and we have our first presenter. How are you,
Perfect.
Roman? And I think we have all the presenters at this stage. It's 3:01. We have 45 people connecting. More people might be connecting, but in the interest of time, I think we need to get started, if that's okay with everybody. So if that's okay with everybody, but let me tell you, it's October 20, 2021, and this is the Quantum Economic Development Consortium, or the QED C. It has a lot of members, corporate, academic, government, national labs, and other, for example, APS is a member. So we are organized in technical advisory committees, or TACs as they are shortened. The TACs are enabling technologies, Q4NS, quantum for national security, quantum law, use cases, standards and performance metrics, and workforce development. This is the workforce development TAC. And this is the last webinar for the year organized by our TAC. The topic is quantum finance. Every second of the month, the chairs and the vice chairs meet with the deputy director and the executive director. And it was August 11 when I was introduced to this particular document, which is coming from the government of Canada. Quantum Technologies Opportunities for 2021. And if you open it, you will find 24 companies that have something to do with the quantum industry. You see a line of businesses color-coded at the bottom. In this table of contents, we recognize D-Wave, we recognize Institute for Quantum Computing, we recognize Zapata Computing, and then we have one qubit ending this table of contents, with Adaptive Finance Technologies being the first one listed. For every company, there are 2 pages. This is the structure for all of them. There's what they do, top 3 things about the company, what exactly they are looking into in terms of making connections. And Adaptive Finance Technologies says that they are interested, for example, in exploring how cutting-edge technologies such as quantum computing could be applied and bring value today in the area of asset management. I want to say a few words at the beginning of every presentation, but I'm done with introducing the first speaker, which is Roman Lutsiv, who is the CEO of Adaptive Finance Technologies. So as they say, Roman, take it away.
Thanks, Adrian. Let me just share my screen. Hi, everybody, and thank you for inviting us to present this event. As Adrian mentioned, my name is Roman Lutsiv, and I'm co-founder and CEO of Adaptive Finance Technologies. We are a Toronto-based fintech specializing in quantum-enabled AI-driven investment management solutions. So a bit about who we are. We were founded as part of the first quantum machine learning program hosted by Creative Destruction Lab Accelerator here in Toronto back at the end of 2017, early 2018. My co-founder, Edward, has a PhD in quantum information and hands-on experience working with quantum hardware, and he's our chief scientist. As well as we hired Jared, who's also a PhD grad from Yale, and he's our data scientist. Prior to co-founding Adaptive Finance, I spent several years working in the finance industry at a Canadian bank. And one of my main responsibilities was devising systematic investment models, which we would then package into exchange-traded products. Also, like during this time, I realized some of the challenges and pain points that the industry was facing, which now we are trying to solve for. So financial markets to this day exhibit distortions and inefficient tendencies stemming from a variety of issues, be it the behavioral biases persisting in active management, fear and greed and herding mentality causing overestimation of both upside and downside potential, or static models that fail to adapt to constantly evolving market dynamics. Perhaps it's unsurprising then that portfolio managers have struggled to outperform and beat their benchmarks, which has been part of a wider trend of downward pressure on the revenue for the industry due to lower fees and AUMs. While at the same time, costs have been rising because of technology and increased regulatory spending. So the industry has responded by investing into increasingly quantitative investment approaches, AI, and now more recently into quantum technologies. But these trends pose challenges themselves, mainly time and money. It takes a lot of time and money to find, train, retain, and keep a talented team of AI and data scientists to build machine learning models and deal with its complexities. So basically, that's where we come in.
I'm gonna.
It's really tricky because you have to the person.
Sorry, there's somebody in the background.
Might need all of a sudden like 20.
John, if you can just mute,
like you've been asking for like 5 in the last 10
John,
rounds.
if John can mute
20.
everybody.
So I've been anticipating that you needed 5 or whatever. And then you make, because then you have to order
hey,
more.
Tom Hoskin,
Like,
can you mute yourself?
And so it's kind of random because.
So very good.
Oh, right. Yeah, so basically that's where we come in. We are developing a SaaS platform for investment professionals, providing them with analytics tools to help them manage their portfolio better, navigate markets more efficiently, discover new opportunities, and capture alpha. It will enable users to automatically build custom hybrid machine learning models based on their specifications. And prior knowledge of machine learning or quantum computing for the end user is not required. Our solution can be used to complement and integrate with existing investment management decision-making process, or used as a primary tool for portfolio construction. These tools have been built on a framework utilizing quantum computing and classical ML that we have developed, where our machine learning algorithms are trained by a hybrid system involving quantum annealing and classical optimization methods. For quantum hardware, we're currently using D-Wave's Advantage system. So to show that our technology works, we have developed a fully systematic investment strategy, which is solely underpinned by this framework that I have just described. It's a long-only strategy, and it focuses on the US large cap market. So basically, S&P 500 constituents. We did a backtest, and after seeing promising results, have decided to put in our own capital into the strategy and have been running it live for over 2 years now. And you can see some of the performance results on the slide. Next, in terms of technology stack, most of our staff resides on AWS cloud with connectivity to Adolphs quantum annealer. And we plan to offer access to our solution through a web-based application and API, and in the future through financial data terminals and cloud platforms such as AWS or Microsoft Azure or Google Private Cloud. This one is a bit of a loaded slide, sort of Quantum 101. I just wanted to say that for us, using even present day state-of-the-art quantum hardware such as that from GWAVE can already lead to several advantages, such as improved accuracy, especially when dealing with smaller data sets and sparse data, more resistance to overfitting, or a greater interpretability. And some of these findings have been confirmed by others and published in scientific journals. And that's it for me, actually. Thank you. If there's any questions, happy to take them.
So if anybody has any questions, you could ask them, or you can write them in the chat. So
I'm gonna stop sharing now.
Yeah, here's a question that I said I'm going to ask everybody. What, in your opinion, are the needs of the quantum finance industry? And specifically, what kind of workforce needs does your company have?
Yeah, so we plan to hire, hopefully soon, more people on the quantum front, as well as kind of, classical data scientists and machine learning scientists. We find that, sometimes there's, it's hard to find somebody who kind of can be skilled at all of the different trades, right? Those scientists are few. So like having both data and classical machine learning as well as quantum I think is very important.
As a follow-up, although if anybody has any other questions, just go ahead and ask them or put them in the chat.
I have a question.
Yes.
Adrian. So you mentioned that I think you're using D-Wave systems today, and those are provide some advantage as gate-based systems improve. How hard will it be for you to take advantage of that type of capability? Can you migrate what you do on the D-Wave to others, or do you have to sort of start from scratch? Are you anticipating and running things on simulators today? How are you looking at other types of quantum computing capabilities?
Yeah, we're definitely actively looking into developments in the gate-based ecosystem, and in our roadmap in the near to medium term, we definitely plan to kind of experiment with the gate-based systems as they develop further. It won't be it won't be redoing everything from scratch, but there will be some changes that will be needed to to be incorporated. But yeah, we're definitely actively following what's happening. But GWAVE actually recently announced that they're planning to start work on their gate-based system, and then there's been recent announcements from IonQ and the others. So yeah, we're in our roadmap, we're definitely aiming to sort of start experimenting in the near to medium term.
So Roman, this is Chris, wondering like what the addressable opportunity is, like who are your clients? Can you share any insight into who's using your systems and who you're targeting as next set of clients?
Yeah, so this is more of for kind of professional investment management crowd. So portfolio managers, analysts who are actively involved in building and then rebalancing portfolios on periodic basis, and especially the ones who have already incorporated or are incorporating some of the kind of more quantitative methods would be kind of our number one primary sort of user base. But as I mentioned in my presentation, even more kind of traditional fundamental portfolio managers, I think now are kind of becoming more attuned to developments in the kind of quantitative field.
Great, thank you.
Okay, with many thanks to Roman, we're going to move on to the second presenter. Clemens Adolphs is a senior optimization solutions lead at 1QBit. He has led a number of projects around advanced and quantum computing in finance, insurance, and logistics, both for internal research and with industry clients. He holds a PhD in theoretical physics from the University of British Columbia. Clemens is going to talk about one qubit's place in the quantum ecosystem and explain the company's approach to quantum solutions with a focus on one qubit's work with financial institutions. Go ahead, Clemens.
Thank you very much for that introduction, and I'm very excited to be here and able to present to so many interested people on this interesting topic. So one qubit, our motto is redefine intractable, and we offer advanced and quantum computing solutions. Just a little bit of overview before we get to the actual interesting things. So we've been around for almost 10 years now. Have grown. When I joined, we were 20 people. Now we're almost 150. Lots of us straight out of academia from their PhDs. And okay, here's some numbers about money and patents and papers. But let's get to where we sit in the quantum ecosystem. And our view is that there's a lot of clients in industry that have optimization problems that they could benefit from a better solution. There's a rich hardware ecosystem, quantum computing, quantum annealers such as D-Wave, gate model quantum computing such as IonQ, which I believe we have on here as well. Then there's a number of devices that aren't quantum, but what they do is inspired by what the quantum computers do. So as a special purpose chip there. And we aim to connect these industry problems to the right hardware to solve this problem. And I think Roman also talked about a number of these pain points that exist in industry, which hardware to pick, which how to formulate a problem to take advantage of these special purpose hardwares. And we exist as the go-between of those. So what that means is that we have a number of kind of pillars on the hardware side. We have a lot of expertise in quantum computing, but also supplement that with cloud computing, special purpose hardware chips, think GPU, think ASICs, FPGAs, those kind of things, hybrid systems, machine learning as another important tool of non-classical approaches to problem solving, and then there's classical operations, research optimization, and innovation in the hardware space. On the other side of this picture, then we have worked with industries in a number of verticals. So relevant for this talk is our finance and insurance. There's a lot of overlap between those. But we also have a lot of work in logistics, mobility, scheduling, those kind of things. So how does our quantum computing approach actually look like? So here we have challenges. So with quantum computing, we expect unprecedented speed ups. You might have heard in the news when Google announced their big experiment on quantum supremacy, that on certain problems that are carefully crafted, you already have demonstrable speed ups of quantum computers over classical computers. And then, of course, there's a wealth of theoretical work that says, if you manage to build a quantum computer that is big enough, that has enough qubits, and those qubits are stable, then you will get this exponential speed up. Or in some other cases, like some of the papers that will be discussed today, you get a quadratic speed up, which is still very useful in practical applications. The problem is that quantum computing is hard. Not every problem will benefit from quantum computing. So sometimes in the media you hear, oh, a quantum computer will just run everything in parallel and everything will be faster. It's unfortunately not quite as easy. So the mathematical formulation needs to be appropriately developed. The appropriate hardware needs to be picked. Is this an annealing problem? Is this a gate model problem? Which of the gate model candidates is most promising for this type? Because they all have different strengths and weaknesses. And then what sort of performance can we expect? How can we extrapolate from today's performance to what it will do in the future? And finally, how will we deploy all this? So we come in with our approach to the solution. We have our researchers with years of experience in developing these solutions. And we take this all the way from problem ideation to solution deployment. And a big focus on how we work is to really work close with the client, so they don't just give us the task, the problem they need solved, and we come back with a black box solution that does that. But ideally, we involve this knowledge transfer and capability building, because we see a lot of interest in companies that say, we've heard about this quantum computing, we've seen the news and the press releases, we want to start something like this at our company. We would ideally want to start, ideally have some guidance to get us started on that journey. So let me just give one example of how such a partnership looks like with us. So we work very closely with NatWest RBS. There was a name change. So they used to go as RBS, now they're NatWest. And this was a multi-year research and development effort to develop their high-performance computing and quantum capabilities. So we provided our application researchers, ML scientists, optimization researchers. They had the banking experts. Together, we drove a number of advancements in AI and in quantum use cases, specifically for finance, with the joint effort of building up their internal quantum capabilities, so that now they are free to explore and feel empowered to explore this exciting field on their own, relying on their own capabilities. And a big focus on this collaboration was to also unlock immediate and near-term value through the way we design those applications, so that we don't have to wait all the, however many years a fully capable quantum computer is out. So some examples are finding quantum-enabled finance applications based on NISQ, so noisy intermediate scale quantum computers. So basically the devices we have access to today or soon. Quantum annealing is also very important, because both D-Wave it is the paradigm that currently has the most qubits. So it's important to find applications for this, but also because a lot of the classical quantum inspired hardware is targeting the same type of problems that annealing targets. Let me give a few examples of use cases we looked into with RBS. The first one is portfolio optimization on quantum annealers. Without going into too many technical details here, we developed a formulation of this specific portfolio optimization problem, QBO, that is the format that D-Wave wants to get their problems in. It stands for quadratic unconstrained binary optimization. Most problems you find in the real world are not in that form. So some extra brain power needs to go into finding that formulation. And once you have that, you can run it on D-Wave, but also on these classically inspired devices like the Fujitsu digital annealer. Microsoft's Azure Quantum recently came out with a number of these quantum inspired optimization solvers that target the same space. Part of this engagement then again involved this extensive coaching, and they have since gone on and done their own internal research projects using quantum annealing, and they reported, now this is based on their metrics, I don't know exactly what this number means to them, but found a significant speed up over what it was they were previously doing. So this was something that already unlocked some short-term value. We supplement that with kind of a more long-term view of gate model quantum computers, how would portfolio optimization look on those machines. So we developed a framework for that, which works with any gate model quantum processing unit or simulator if you don't have a QPU, based on a technique called the variational quantum eigensolver, with the idea that they would be able to benefit from advanced future hardware. And this is about building their capabilities with a long-term view, so that once these more advanced devices become available, they're not starting from zero. A few additional use cases with different clients or eternally involve quantum hierarchical risk parity, with the idea of clustering assets in a hierarchical fashion, and you can use that to design a very robust portfolio. Some combinatorial optimization where you offset debt obligations or other derivative-based obligations, thereby minimizing collateral requirements. And then with the view on what will be possible in the future, there's some use cases we'll be excited to explore with interested parties. That is a lot of interesting work about pricing derivatives using quantum circuits, both the kind of replacing Monte Carlo type papers, but also some more exotic approaches for directly solving the Black-Scholes equation by transforming it into something that describes how a quantum system evolves over time. There's some work that can be done on complex arbitrage systems. And then even further into the future, when we have hundreds of thousands of qubits, there will be an opportunity to just generally speed up all types of linear algebra operations, anything that relies on sparse matrix inversion with the HHL algorithm. And then there's some research on how you can use quantum annealing for reverse stress testing for regulatory needs, especially with the Basel III and beyond rules. So with that, this list of potential use cases, I say thank you for your time and looking forward to the panel discussion and any questions you might have. Thanks.
A reminder that you can ask questions or you can post them in the chat. Here's my question for Clemens. Could you give us an idea of the range of backgrounds that the people that you said you grew from 20 to maybe 50? Do you hire MS students? Everybody in your company has a PhD. Are they all coming from physics? What kind of people are you hiring or looking to hire?
Yes, what's our makeup? No, so not everybody has a PhD, and we are not elitist about it. We have lots of fantastic members that came to us after their masters or during their masters as university interns and then grew into the role. Backgrounds are physics, computer science, mathematics, operations, research. So those are the main ones that come to mind right now. And physics also all over the place, as astrophysics, particle physics, condensed matter physics. So those are the ones I know more about because I'm a physicist myself.
Thank you.
Mm-hmm.
I had a question. You mentioned earlier that you guys identified some different types of problems that the different types of different types of computers quantum computers can solve. Did you categorize that? Like, are they based on different mathematical problems that you think a quantum annealer is better for versus a NISQ computer? And is that something that you can share?
Yeah, so thanks for that question. Yes, so in particular, our more research focused parts. So I'm more in the customer solutions side of the company, and our research side, they think a lot about exactly your question. I'm not aware that we have something kind of like a nice list of problems that I could just send out. It's more we keep our eyes on research, on the literature. Part of the papers that we'll be discussing today, I understand, deal with this amplitude estimation as one technique that runs very well on gate model quantum computers, and you can use it for finance applications, for example. Yes. There's no simple answer, unfortunately.
Thank you.
Okay, so with this, it's time to move to our third presenter with many thanks to Clemens and in fact to both our Canadian colleagues. Sonika Johri leads the quantum application research team at IonQ, a company commercializing trapped ion computers. She has worked for 7 years in the area of developing algorithms and software for near-term quantum computing. She has a PhD in theoretical condensed matter from physics from Princeton University. Sonika is going to describe some of the more recent breakthroughs that IonQ with Goldman Sachs and QCware have announced. IonQ, of course, is the first publicly traded pure play quantum computing company on the New York Stock Exchange. Go ahead, Sonika.
Thanks for the introduction and the invitation to come and speak here. So I assume everyone can see my screen and hear me talk? Yes? Yes. Okay, awesome. Thank you. Yeah, thanks for the invitation. And I'm going to describe, as Adrian mentioned, a couple of recent papers that came out of IonQ's application team, which I lead. Our team basically, IonQ is a company that is commercializing trapped ion quantum computers. And recently, they've also started focusing a lot more on applications, like building up an applications team, which goes out and works with quantum software, quantum algorithms and software startups like 1QBit, and also directly with end customers and helps them think about how quantum computers can help their business grow. And so just a very short spiel about IonQ's technology. So IonQ's systems are based on ionized atoms, which are held in place in linear arrays by electromagnetic fields that are created by lasers. And atoms are naturally quantum objects, right? So there's no, there's no very advanced fabrication technology that is required to make IonQ's qubits. They naturally exist in nature, and every qubit in IonQ system is exactly the same as every other qubit. So this gives it a high degree of reproducibility and uniformity, which is essential to scale the technology. The atoms are held they basically hover over the trapped ion chip. They're held in space by the lasers, and so they're isolated from environmental influences such as defects in the substrate of the chip. The current systems run at room temperature, so there's no need to build a giant dilution refrigerator which is eating up like the world's limited supply of helium. The system, one very powerful feature of the systems is that even though the qubits look like they're on a line, you can actually entangle any two pairs of qubits, any pair of qubits in the system. And that just, for anyone who's ever designed a quantum circuit and tried to run it, this high degree of connectivity is absolutely, I would say almost essential for many algorithms, like whether you get garbage out or you get something useful out. This high degree of connectivity will make all the difference. And of course, they have, they're the basis, the same technology is the basis for atomic clocks, right? So you can imagine that they obviously have the longest qubit lifetime. So the first project that I'll talk about is something that we did with Fidelity Center for Applied Technology. This was around applying generative learning for finance, and the application, there are many applications which I'll talk about in a second, but basically the problem is, let's say you have a basket of stocks, right? Or it could be some other set of variables. Let's say you have stocks that are Microsoft and Apple, right? And you want to understand how the returns of those two stocks are correlated with each other over a period of, let's say, 8 years, right? So then you can plot this scatter plot. Now you don't want to understand, you don't want to fit just one number to the correlation. Like you don't want to fit like a simple line, or just do a simple Gaussian fit of the correlation Gaussian fit of this scatter plot, but you really want to understand the multi-point correlation function between these two stocks. And a very modern way to do this is by doing generative learning. So training a generative model that can produce samples from this probability distribution. And typically that will be done. There's a mathematical concept in probability theory called copula functions. And typically this generative learning would be done using copulas. And so we decided to apply quantum generative learning to that. And we mapped this copula function to maximally entangle states and then theoretically prove some properties of that. And then we ran it on the actual quantum computer, and it compared the quantum generative learning to the equivalent classical models. And you see over here the results, right? So qualitatively, the first thing you notice is that the classical models just take way longer to train than the quantum model. So this was the classical GAN trained in about 20,000 iterations. So this is the same number of parameters in all three. And then the quantum model, the quantum GAN trained in about, the GAN is the generative adversarial network. It trained in about 1,000 iterations. And then another model called the quantum circuit born machine trained in just about 20 iterations. And then let's just qualitatively look at the quality of the data generated by the three models. And you can see that the classical GAN completely misses, like it just doesn't look like the real data at all. And very significantly, it completely misses the data and the tails of the distribution. So this is very bad, right? Because for instance, people say that, that 2009 financial crash was actually caused by people missing things that happen in the tail of distributions, right? So you miss all the rare events. There's the quantum models easily capture those, right? And then you can also apply some statistical tests to the different models, right? And you can see even the ones that we ran on the actual quantum processor, it was just 6 qubits. They outperformed the equivalent classical models quite handily, right? So this was very successful. And we were talking to Fidelity, and it says in this paper that once you're at about 50 qubits, algorithmic qubits, they don't have to be logical qubits, just 50 algorithmic qubits, you should be able to, you should be able to do, let's say, a basket of 10 stocks, right? And then you can understand their correlation function, and then you can also use it for instance, the first speaker was talking about backtesting financial models, right? So you can use it to generate data to backtest your financial models and things like that. So we expect that this is going to be a very powerful technique in general for finance. Then another recent paper that we had was doing amplitude estimation, which is the basis for most Monte Carlo based, it is the basis for speed ups in Monte Carlo algorithms. It's the basis for quantum speed ups in Monte Carlo algorithms. And we basically, we compared classical sampling from an evaluation oracle with a more quantum way of sampling, which was based on quantum amplitude estimation. And we compared it on both, we ran it on the current generation IonQ quantum computer, which is on the cloud, and also our next generation IonQ quantum computer, which is available for certain partners. And this was done in collaboration with Goldman Sachs and QC Ver. And you can see that we basically saw that by using the more quantum technique, you could get a 70% error reduction compared to classical sampling. And then this was basically, this is a building block of all kinds of applications in finance, such as risk analysis and price simulation and so on. And the interesting part was, so there was a theoretical paper before this on amplitude estimation from Goldman Sachs and QC Ver. And they had done some analysis on basically making quantum amplitude estimation more near term by using maximum likelihood estimation techniques. And what we found was very interestingly, because while seeing full-blown quantum advantage using amplitude estimation is still far off, like you need lots of qubits, but the same techniques can be used on near-term quantum computers to reduce the error that happens due to noise, right? So you can go past the noise threshold, right? Because your qubits are not perfect yet. You can power past that by just applying these amplitude estimation techniques, right? So that was also a really interesting finding. And then I just briefly want to end with recently the QEDC, it put out this paper on benchmarking and thinking about how do we evaluate what quantum computers can do when it comes to applications, right? And for a long time, the community was focused on device level benchmarks like number of qubits, fidelity of gates, and those are useful, but doesn't really tell the user what you can do with the quantum computers. And so we came up with this repository of algorithm level benchmarks, and it's available on GitHub, and anyone can go and use it. And IonQ contributed data to that paper, which was on its new system, which has up to 21 qubits. The data had up to 21 qubits, and it had extremely high fidelities all the way up. And so basically, I'm pretty excited that the community has now moved to a phase where we are now looking at algorithm level benchmarks. And IonQ, of course, plans to keep scaling up its number of qubits and also increasing the fidelity of the qubits. And we see different, different applications are going, this is our current view of how different applications will be enabled at once we reach certain numbers of qubits. And of course, now we have the benchmarks repository to kind of measure progress towards that. So I'll end on that note. Any questions?
Wonderful. Thank you so much. Any questions? Yes, either in the chat or just ask them. I promise.
Maybe then a quick question for me.
Yes, please go ahead. Go ahead.
Seeing the slide with the expected number of qubits, so different designs, of course, will be like easier or harder to scale. Now, if your ions are all in a line, I guess doubling the length of the line isn't that hard. But can you talk about what that does for the qubit to qubit interaction? If you have like 1,024 qubits at the ends of the chain, you now need to get them together to interact. Does that pose any problems for your technology?
Yeah, so the way we scale up is that you probably won't put 1,000 qubits in the same chain, right? So you grow your chains up to a certain number of qubits, and then you go to more than one qubit chip, which is coupled by photonic interconnects. And so within one qubit chip, you have all-to-all connectivity, right? And so now if you have more than one qubit chip, you still have all-to-all connectivity, but at most you have to do two operations to get all-to-all, right? So one across the photonic interconnect, and then you have all-to-all, right? Does that make sense?
Oh, absolutely. Yeah, thanks.
Hello. Hi, I just have a quick question in terms of your mentioned that your iterations or your quantum CBM was faster than the classical GAN model. And I just wanted to just clarify if that is just per iteration basis, or is that per the whole training basis?
So it just took fewer iterations, right? When I say faster, I mean that it took fewer iterations. So fewer calls of the cost function.
Okay, thank you.
Sonika, did the iterations take the same amount of time across the different methodologies?
No. So the quantum one is slower for now, for sure.
Got it.
So yeah, I forget the exact numbers, but if you look if you go to the paper, we have the exact run times for all of them, right? For now.
Thank you.
So with this, we're ready to move to the last presentation for the day. So thanks, Sonika. And Lawrence Gasman is president of IQT Research, which is the research wing of Inside Quantum Technology. He has spent almost 45 years analyzing commercial potential for new technologies and has written 4 books on this topic. He was educated at the University of Manchester, London Business School, and the London School of Economics. Lawrence will discuss IQT's new report, analyzing the opportunity for quantum computing. The report includes profiles of the internal quantum computing development work being done at 18 leading financial institutions. Go ahead, Lawrence.
Lawrence, you're muted. You'll need to click the unmute button, please.
There we go. Can you hear me now?
Yes.
Thank you.
Excellent. So I am the president of IQT Research and Inside Quantum Technology. For those of you who don't know us, Inside Quantum Technology is a media company dedicated to providing information to the quantum technology market. We run conferences. We have a large conference coming up starting on November the 1st, goes on for a week. And one of our featured sessions, for I think about 2.5 hours, is on financial use of quantum computing. We have some great speakers, so I recommend that event to you. We also have a daily newsletter, which is just about to turn into something a little bit more ambitious. But we also publish reports on market opportunities in quantum computing and other aspects of quantum technology. And that's what I'm going to talk to you about today, a study that we brought out on the opportunities for quantum computing specifically, a little broader in places, but mainly quantum computing within the financial services industry. Most of our reports in the past have been about quantum technologies, whether it's quantum safe technology or quantum sensors. This is our first user-directed one. So why pick financial services? Actually, the biggest application for quantum computing at the moment is probably R&D. Well, actually, no probably about it. It is R&D, whether that means working on quantum computing itself. So there are a lot of subsystems that aren't quite quantum computers, but are good for working on, that are around. And then people do interesting experiments using quantum computers at universities, think tanks, whatever. But although that may represent about half the activity in quantum computing now, presumably everybody who's here is here because they think it's going to go a lot further than R&D. I certainly am. And we think that financial services is probably the one where there will be a takeoff point and there'll be significant revenues generated by quantum computing. There's some ifs and buts about intelligence services and military applications, but by definition, we don't know much about that. So we picked financial services. And that report, by the way, I'm only going to delve into it, obviously, in the next 10 minutes or so, is available on our website. The pricing is up there. You can buy it directly from the website. You can give us a call. Our website, not surprisingly, is www.insidequantumtechnology.com. But first thing I should say is it's very nice. This is going to be the first revenue generator of any significance, but there really isn't much being generated yet. And one reason is that there's lots of interesting stuff going on in banks and other financial services involving quantum computing, but very little that's user-facing yet. And one reason for that is obviously, would you really want your $20 million portfolio entirely dependent on something quite as new as quantum computing? Bad things can happen, and it's going to be a while, and there's going to have to be marketing efforts by the banks before this really takes off in a completely commercial way. There are probably, we estimate, about 40 financial institutions, mostly large ones, working on quantum computing internally. Most of them are banks, but there's credit card companies like MasterCard that are working on them too. And you'll hear some of them if you come to our conference in 2 weeks. In the study, we profiled about 20 companies, mainly banks, some other financial institutions, and also a select group of really quite small companies who do internal work, financial work on many things actually, but using quantum computing online mostly. We have a panel on them in particular, and it's called Quantum for Quants, and that's kind of describes what I'm talking about there. So the report is divided between the profiles, which give a very good indication of what's going on now and what the banks hope is going to go on in the future. We interviewed, actually, I don't know, to tell you the truth, we did about 25 interviews with banks, and much of that is reflected in the profiles. We also have several sections on how far this can be taken, what the time frame for different applications are and why. And we also have a forecast on our expenditures, which I'll close off this talk with. I keep on switching backwards and forwards between banks and general financial institutions. So maybe I should be clear. The place where most of this is going on is actually in big banks. And it's very interesting what they're doing. I mean, the thing that surprised me a little when we did this is the teams that they're building up. We constantly hear how hard it is to get quantum competent people to come get to work for you. And obviously we're talking about PhDs, we're talking about people who earn a pretty decent sum of, living wherever they are. And a lot of these people really fit into that. I mean, they're very senior employees. They come sometimes from big computer companies. So the big banks aren't playing at this. This isn't like one person sitting in a room and being a quant or being a nerd. It's serious teams. And maybe I shouldn't say who it was, but I was actually at another conference and went to breakfast and kept on bumping into people who worked in the quantum department at a big bank. And by the time I'd finished breakfast, I'd literally met 5 people, which was, in terms of the particular bank, was a tiny fraction of their total staff. But to have 5 senior people in quantum showed that this is a very big deal. And this is one of the reasons we think it will be one of the big areas for quantum in the future. The other one being, when you look at our list of possible applications for quantum, and I will go into that in a minute or two, but I can't give you the complete list because it would have taken the whole 11 minutes of the talk I'm supposed to be going. I'd still be listing it at the end. Maybe that would be useful. And anyway, I think you get that information for free on our website once when we think it is. But one of the big ones in the medium term is portfolio management. Again, not quite ready for prime time for the reasons I mentioned, that not at the moment. There's a sales job to be done on, getting big corporations and entities like that to actually want their portfolio to be optimized on quantum. There's some risks there if things go badly wrong. Oh, you used a new technology. There's regulatory issues too. To state the obvious, the banking industry is one of the most regulated industries in the world because, every country, maybe there's a few exceptions in the Caribbean or somewhere, but regulators are very much on top of everything that bankers do. So there's not much freedom. So this is going to take a while to develop. How long, I'll talk about in a minute. And perhaps even the management in the banks themselves are not quite ready to make this free and open. But there are some things that are, and I think they're characterized by not being customer facing. And we've already heard quantum and machine language talked about in the same breath, actually, last speaker. And that's one of the areas we expect to take off first. And the other area, and that we're seeing a lot of interest by the banks, and this actually may be a fault with our survey, because I didn't realize when we commissioned this that we were, with our analysts, that we included quantum, quantum safe technology. But the immediate interest in quantum technology by some of these financial institutions actually is protecting their data from quantum computers. So it's kind of protecting against the quantum dark arts. It'll take a little longer before they're actually doing something positive. Now, in terms of deployment, we have a very nice graph in there, which I think is very useful to think about. So where are we now? Basically proof of concept. People are trying new things all the time. They've got some very, spent a lot of money on all of this, both on personnel and on hardware, but right now it's just proof of concept. How many years before they start doing something useful? Well, probably no more than 1. We have 1 to 3 actually. You'll start seeing little things appear at the very big banks. What's the big constraint now? Well, certainly regulation, but the other thing is basically hardware constraints. And again, you've heard this, there's some fascinating things you can do with quantum technology, but you just don't have enough qubits. And that's really changing. I mean, it's not much more than a year before when there were papers appearing in fairly respectable journals saying that quantum computing was actually impossible, because you'd never be able to get stable enough qubits or enough qubits, and we're obviously past that phase. Nobody would publish that now. But still,
Lawrence, just a quick question. There's 1 minute left, more or less. Did you want to share any slides?
I don't have any slides. No.
Okay, that's fine then. So
okay.
About 1 or 2 minutes, and then maybe questions and
yeah.
Perfect.
Okay. A lot of that's going to improve. I also think, and this is a conversation for another time, you're going to start to see smaller quantum computers that will gradually allow quantum computations appear with smaller banks, smaller financial service companies, consultants and the like. I'm not talking about, quantum PCs or anything. At least I don't think I am, but something less than a $15 million machine. So you'll see, I think, this technology within the financial services community deploy down to smaller institutions. If you take a look, even at the table of contents of our report, you'll see that all the profiles we've got are of almost household name companies. And that's where a lot of this is going on at the moment. And just one final thing, what kind of numbers are coming out of our analysis? And I'll spare you the methodology because we have a limited amount of time. Basically, for the banks, specifically for the banks, we think in 2026, so when things are still, more developed than they are now, but a long way from where they could be, about $350 to $380 million will be spent by banks on hardware for quantum. And that assumes that there's some, non-$15 million computers out there. And that would be a general trend in computing in many other areas too. And probably about half of that is coming from North America, which should be no surprise. That's where the banks are. And about a quarter from Europe. A big question mark over China. We really don't know. We have some numbers in there, but there's so many ifs, ands, and buts about China that, we have actually forecast. We don't feel entirely certain about those numbers. Maybe we need a quantum computer. So, and that is that. Thank you very much.
Okay, so if we have any questions, we have 1 minute left for questions.
I have a sort of, I guess it's a non-technical question, but Lawrence, this may be for one of the other speakers, but your remarks about the regulatory environment in which this sector operates made me sort of think also of biomedical, where of course drugs are heavily regulated, but wellness tools and things that monitor your, exercise level or something is not so regulated. So in the finance space, one qubit or adaptive finance be targeting tools that are, not necessarily controlling your investment, but giving you useful information that you can take or leave, for educational purposes or something. Is that a market that's different?
Yes.
The banks
Yes.
themselves?
I think that, so there's a group of companies that are helping banks and financial services. They're the quants, they have access to quantum computing over a cloud or whatever. And they're doing, they're doing math inside the institution. And that in itself isn't really regulated. So there's going to be a lot of that going on. The big money is obviously in things like portfolio management. I mean, that's why Goldman Sachs got big. So there's some very early stuff, and we do talk about that. And absolutely, there's going to be that. I mean, even it's difficult to know without being very fine-tuned on this, and that's in the report. But you're making the point about medical devices. Even little medical devices are regulated at some level, even if it's just product regulation. So you'll never get away from regulation, but I don't think people want to go, companies who want to make money quickly, if you like, are going to go into the really big areas like this at the moment. And as I mentioned, one of the little facts that came out of this was that quantum security is a big issue for them, and that doesn't really require regulation in quite the sense that I think you meant it, Celia. So I hope that answers your question.
Thank you so much. This brings us at the top of the hour. So I want to thank the 4 speakers that were kind enough to come here and present, and also to everybody who joined us today. This was our last webinar for the year. We have one more e-poster research session on November 2nd, elections, and then we're going to meet in person at Q2B 2021 in Santa Clara. With this, thank you so much, and I hope you have a wonderful rest of the day. Bye-bye.
Bye-bye.